Hello everyone, this is Vijetha, Associate Professor in the Department of ECA from MLR Institute of Technology. In this video, I would like to talk on delays, how to implement delays in gate level designing from linear and digital integrated circuits. So here, first delay, I would like to talk on net delay. So, Verilog facilitates to account for different types of propagation delays. And these delays can cause a distributed nature of its resistance and capacitance. Now, the first delay which I wanted to speak here is net delay. How to implement a net delay in a gate level. This is one of the simplest delay that can be given with a net, and it can be a part of declaration statement. For example, wire is a net type. This #2 represents a delay and NN is declared as a net with a propagation delay of 2. NN is a variable, and this variable can be declared as a wire with a 2 time intervals of delay. And the same delay can be given with wire #2, 1 and M. NM is a variable which is assigned as a wire with a delay of 2, 1. What is 2 and what is 2? What is 2 and what is 1? Here, this #2 is a delay for the propagation delay for both the positive values as well as for negative transition. But here, this is for a positive transition. This 2 is a delay for a positive transition, and this 1 is a delay for a negative transition. What is positive transition? What is negative transition? When your NM value is changing from 0 to 1, then it takes 2 time intervals of delay. The changing of the value from 0 to 1 is nothing but a positive transition. And here, when NM is changing from 1 to 0, it takes a time interval of 1 time intervals, delay of 1 time intervals, and changing of this value from 1 to 0 is nothing but a negative transition. So, the first delay which I am speaking here is net delay, which can be declared either as a single delay for both the positive and negative transition, or you can declare the different delays for positive and negative transitions. Here, it has been explained with the pictorial representation. See here, I am declaring a net NN between the circuit 1 and circuit 2, which is, and this is a common ground for both circuit 1 and circuit 2. So, I have given a X value as 0, again it goes to 1, again it goes to 0. This is what it is happening. This is the input. But you need to get the output as it is. But as I have declared this as a #2 and N, it works with a 2 time intervals of delay. So here at time t is equals to 0, I gave the input value is 0. So it will be same at time t is equals to 0. But this 0 will be there at the output side till 2 time intervals. See here, here the transition have been occurring from 0 to 1 here. But here it waits for more 2 time intervals, and after the 2 time intervals, the transition is going to be occurring. Again, here the transition is occurring from 1 to 0 at some time t is equals to 6. Let us assume that at time t is equals to 6, the transition of 1 to 0 is going to be occurring at the input side. But it waits till 2 more time intervals, that is at time t is equals to 8 at the output side, the transition is going to be occurring from 1 to 0. So, this delay will be provided by using this net delays. Now, the other example here is wire #2, 1, N. M. So, NM is a variable which has been assigned to this wire, that is to drive the output of circuit 1 to the input of circuit 2. I use a wire with the name of NM, and which has been given with the delay of 2, 1. So, this 2 is a delay when it is a positive transition, that is from when it is moving from 0 to 1. And this 1 is a delay when it is moving from 1 to 0. This is a negative transition. So, here at the circuit 1, initially it starts with 0, and let us assume at time t is equals to 1, the transition have been occurring at this from 0 to 1. So actually at output side also at time t is equals to 1, it has to occur with the transition. But as I have mentioned, there are 2 time intervals for a positive transition, that is 0 to 1, that is positive transition. It has to wait for 2 time intervals. That means at time t is equals to 3, the positive transition occurs at the output side. So this happens. And here when it is negative transition, that is from when it is moving from 1 to 0, let us assume that at time t is equals to 7, the negative transition is occurring at the input side. But as I have mentioned that this net has to wait for one more time interval to go to the circuit 2. So at time t is equals to 8 at the output side, the negative transition will be occurring. So this 2 represents the delay for a positive transition, and this 1 represents the delay at the negative transition. This is how a net delay can be implemented. The few examples have been taken for the net delay here. See here, I have implemented a wire hash 2 NN, and here wire hash 2 comma 1 NN. So here simply I have taken a NOT gate, and for this NOT gate I have attached a buffer, and this NN is a wire which is connecting the NOT gate and buffer, and X is an input, Y is an output. For this module, a program have been written with the net delay. So for this module, the module name is given as a net delay, and ports have been declared with X and Y for both these things here, X and Y. Inputs are declared with the X and Y, X, and outputs are declared with the Y. But here I have declared this delay as 2 time intervals, either maybe a positive transition or maybe a negative transition, and I call the NOT, and output of the NOT is taken into a wire NN, comma, inputs are X and buffer output is Y, which is equals to X, buffer is equals to Y is equals to X. So this is buffer, Y is equals to NN, and module. Here instead of writing a single net delay, that is instead of using a same delay for both positive and negative transition, here for positive transition I have taken a 2 time intervals of delay, and for a negative transition I have taken 1 time interval of delay. If you can see, the test bench is same for both the things, but only if you can observe the output, it waits for 2 time intervals whether it is a positive or negative transition, but it waits for 2 time intervals for the positive transition and 1 time interval for the negative transition. That is the difference between these two statements. The next delay is gate delay. So you can implement the delay for the gates also, and this can be specified as a part of instantiation. See here, AND gate is a primitive. This primitive has been given with the name of G, and this is a port list. So this hash 3 is a delay which can be implemented with the primitives also. Here the same thing, the 3 represents the delay, either may be a positive transition or maybe a negative transition for both A, B, C. And here the 2 comma 1 represents the rise time delay, that is positive transition delay, and 1 represents the negative transition delay or negative delay for both A, B, C. The same concept is same, that is a single value. If you can represent a single value, if you can represent a single delay, the delay is for both positive and negative transition. If you are mentioning the delay, then this represents in a 2 coordinates, then this represents a delay for positive transition and negative transition. And the example they have taken for single transition and also for dual transition example have been taken here. So for this they have taken module gate A1, B, C, B1, C1 are the ports, where B, C, B1, C1 are the inputs and A1 are the outputs, and OR gate. So OR operation have been implemented between C1 and B1 stored with A1, and AND operation have been implemented between C and B and which have been stored with the A. So A and A1 are the outputs, B, C, B1, C1 are the inputs, and this has been end with the end module. If you can see, initially at time t is equals to 0, B0, see here, B0, C0, B10, C10, B0, C0, B1, so I have taken only the B and C value, that is for AND gate I have taken here for explanation. So for AND gate, A is an output, B and C are the inputs. B value and C value are given with the 0 at time t is equals to 0. So the operation for 0, 0, the output of AND gate will be 0. So it has to give the output 0. But if it is a positive, see this is 0. Until it get a positive transition, it waits in the 0. See, after 5 time intervals, I asked to change B value and C value to 0, 0, and again after 5 time intervals B1, C1, so total 10 time intervals. After 10 time intervals, B value and C value will be changes. So here, see, B value has been changed to 1 here at time t is equals to 1, let us assume, and C value have been changed here. The transition has been occurred at time 2 time intervals. It waits till 2 plus 2, 4th time interval. It waits here till 4th time interval because the rise time delay which I have mentioned is here, 2 here. So it waits for more 2 time intervals to have a positive transition. And coming to a negative transition, here see, if you can see here, let us assume this has been occurred at some 6 time intervals, but it has taken 1 time interval of delay and it executes at 7 time intervals. It takes a negative transition at 7 time interval. So this is how the positive transition delay and negative transition delay can be analyzed in a waveforms. Just here I have taken an AND operation to explain, and similarly can be applied for OR also. And you can apply the other delay is tri-state the other delay is delay with the tri-state gates. You know that we have 4 different types of tri-states, that is buff if 0, buff if 1, not if 0 and not if 1. These are the 4 different tri-state gates which are there in the Verilog. But here for example I have taken a simple buff if 1, that is if the condition if control pin is 1, that is if control pin is 1, then only whatever the data which is there here will be implemented at the output side. So we know that we have 4 tri-state gates which are buff if 1, buff if 0, not if 0, not if 1. But for here I have taken buff if 1 as an example. And here if the control pin is 1, then only the output will be followed with the inputs, that is AI can be stored in a A0. And this buff if 1 is a primitive for a tri-state gate. This is not hash, this is hash, not at the rate. And B1 is the name of the buff if 1. A0, AI, C are the port names. And this 1, 2, 3 represents the delay. This 1 represents a 0 to 1, that is positive transient delay. And 2 represents the negative transient delay. And this represents the delay for the output to go Z state as C changes from 1 to 0. And this can be implemented for remaining 3 also, remaining 3 tri-states. All 4 tri-states can be implemented with this kind of delay. This is for positive transition, this is for negative transition, this is to change the C value from 1 to 0. So these are the few examples they have given here. See here 2, 3, 4. 2 is a positive delay. See A2 is a control pin, A1 is an input, A0 is an output. A1 will be given to A0. Sorry, this is an AND operation. We can apply for the AND gate also. For this AND operation, this is A0. A0 is an output. It performs an operation between A1 and A2. So 2 represents the positive transient time delay, and 3 represents the negative transient delay, and 4 represents the delay for the output. So it takes 4 time intervals to perform the AND operation and to store in the A0. And here also this is for positive transient delay and this is for the negative transient delay. See here 0 to 1 transition of output, that is rise time. The gate has a minimum delay of 1 nanosecond, a typical value of 2 nanoseconds and a maximum delay of 3 nanoseconds. Similarly, for the fall time, this is for rise time, and for the fall time 2 will be a minimum delay, 4 will be a typical delay, 6 will be a maximum delay. So these are the different types of delays. Here in this video we have discussed about 3 types of delays. The first one is net delay, the second one is gate delays, how to implement the delay in a primitives. The third one is tri-state gate. The third one is tri-state gate delays. In net delay, you can simply give the delays for the wire, whereas in gate delays, you can give delay between the gates like this. And for tri-state gates, you can implement a maximum delay, minimum delay, as well as for transient delays can be implemented. Here and here you can implement for positive transition, for also for the negative transitions. Thank you.